Solution for tutorial 3 question number 1. So there is a composite wall of a oven consists of 3 materials, 2 of which are known thermal conductivity. So for material A, thermal conductivity given 20 watt per meter Kelvin. For material C, thermal conductivity given 50 watt per meter Kelvin. Also the known thickness for material A, thickness is given 0.3 meter, and for material C, thickness is given 0.15 meter. Now in the third material B is sandwiched between material A and C, is a known thickness, so you thickness for material B also given 0.15 meter, but thermal conductivity is unknown, so Kb is unknown. Okay, now the under steady state operation condition, measurement reveal the outer surface temperature is 20 degrees Celsius and inner surface temperature, so Ti, is 600 degrees Celsius. And oven air temperature, say oven air temperature T alpha is given 800 degrees Celsius. Also the oven inner convection heat coefficient given is 25 watt per meter square Kelvin. Now what is the value of Kb? So we'll find out the material B thermal conductivities. Okay, so this problem we will solve based on some assumption. First one is the steady state condition. So assumptions. Assumptions are steady state condition. Second one is the one-dimensional condition. One-dimensional conduction, and the constant properties. Also, will ignore the contact resistance. We'll ignore the contact resistance between material each other. So contact resistance. Resistance is negligible. And another will ignore the heat loss due to the radiation. So radiation effect say radiation effect is negligible. Okay, so these are the given parameters and these are the assumption. So now I'll draw the thermal circuit. Say thermal okay the oven inside temperature, so T alpha, then heat will transfer through between oven air to the oven inner surface due to the convection. So convection thermal resistance will be the 1 over convection coefficient and area. Then the temperature of the oven inner surface, say open surface temperature inner side, then there will be the conduction, heat will flow from through the material A. So thermal resistance for material A, so length for material A over thermal conductivity for material A and the area. Okay, then the material B, thermal resistance, so length for material B, thermal conductivity for material B and the cross-section area. Then the material C, thermal resistance, so length for material C, thermal conductivity for material C and area. Then the outer surface, open outer surface temperature. So say it will flow from open inside to the outside direction, heat flow direction. So now we can calculate how much heat will transfer through the composite wall, say through a composite wall. Heat transfer due to the conduction. So basically between this portion will be equal to temperature difference divided by total thermal resistance for through the composite wall. So here temperature difference is T oven inside temperature minus T oven outside temperature divided by total resistance for material A, thermal resistance for material B, thermal resistance for material C, thermal resistance. Now heat flux. So heat flux will be for the per unit area heat transfer. So Q through the wall divided by area. So Q value from here. So we can write down say 1 over A times Q is say T surface inner minus temperature open surface outer, and we can write down like say L A K A 1 over K. So 1 over A, if I take the common, the area, so length for material A, then divided by thermal conductivity for material A plus length for material B, then thermal conductivity for material B plus length for C divided by thermal conductivity for C. A. So we can take common 1 over A. So this now, this A will cross out. Now if I put the all values, so it will be the heat flux. Now there is an inside temperature, inside wall temperature for oven is given much given 600 and outside is 20. Okay, so 600 minus 20, and length for material A is given 0.3 meters, divided by thermal conductivity is given 20, plus length for B is given 0.15, and thermal conductivity for material B is unknown. We will find out this one. Material C length given 0.15 and thermal conductivity given 50. So from here we'll get the heat flux through the composite wall. It will be 580 0.018 plus 0.15 K for material B. So this one is the heat flux through the composite wall. Now we can say for here, this inside oven temperature bit will transfer through from oven air to the inner wall through the convection. So here will heat flow through the convection. So convection heat transfer between oven air and the inner wall of the oven. So we can calculate the convection between the oven air and inner wall. So heat flux, so it will be a convection, so a coefficient of convection, then your oven air temperature minus inner wall temperature. So we'll get here H is given 25 and oven air temperature given 800 minus inner temperature for inner wall temperature for oven given 600. So it will be 5000 watt per meter square. So basically this heat flux will transfer through the oven air to the inner wall, then the same amount of heat transfer will transfer to the composite wall also. Say we can write down here, say from this equation, say 5000 equal to 580 0.018 plus 0.15 thermal conductivity for material B. Now if we solve this one, we'll get our required answer. So material B thermal conductivity will be 1.53 watt per meter Kelvin. Okay. Yeah, straightforward problems. Okay, now I'll solve the question number 2. This one also related to thermal resistance, but for cylindrical coordinate problems. Okay. Okay, so thin electrical heater is wrapped around the outer surface of the long cylindrical tube, and inner surface is maintained at a temperature of 5 degrees Celsius. Okay, so inner surface of tube temperature is maintained 5 degrees Celsius, and the tube wall has the inner and outer radius. So inner outer radius for tube wall given. Inner radius is 25 millimeter, outer radius 75 millimeter. And also thermal conductivity for tube materials given 10 watt per meter Kelvin. Now there is a thermal contact resistance between heater. So this on the heater. So between heater and the tube, there is a thermal resistance given between the tube surface and the heater. So here in this look area. So this contact resistance given 0.01 meter Kelvin per watt. Okay, now outer surface of the heater is exposed to the fluid with negative 10 degree. So outer surface heater fluid temperature given negative 10 degree, and convection coefficient of heat H given is 100 watt per meter square Kelvin. Determine the heater power per unit length. So determine the heater power per unit length of the tube required to maintain heater at 25 degrees Celsius. So your heater tube temperature given 25 degrees Celsius. So heater power, determine the heater power per unit length of the tube required to maintain the heater at 25 degrees Celsius. Okay, so already I marked the given parameter. So this problem also there's a some we'll solve some based on some assumption. So assumptions are, say first one, say this one is steady state condition problem. So steady condition, and this one also one dimensional conduction problem. Then constant properties, thermal conductivity, other material properties are constant. So constant property, properties, and we will ignore the radiation loss, negligible. Okay, Okay, another one is negligible temperature drop. Negligible temperature drop across the heater. Okay, so first I will draw the thermal circuit. So inner temperature, then the tube material, so conduction, heat transfer, here will be conduction, heat transfer, so thermal resistance for cylindrical coordinate, so log outer radius divided by inner radius over 2 pi k. This one in terms of per unit length thermal resistance. Okay, then we have the contact resistance between heater and the tube, say R thermal resistance for contact, then heater temperature, heater will maintain 25-degree temperature, then we have the temperature heat flow from heater to the fluid, outside fluid, so it will be the convection. So thermal resistance for convection is 1 over convection coefficient, then pi diameter, so outer dia, and here is the environmental temperature T alpha. Okay, so here heat source is the heater, so heat will in here, the heat source, the heat in, say for per unit length, and this heat will flow or transfer from O2 in this direction, say heat flow per unit length, say in towards the B, and this one is a heat flow per length towards the A. So okay, so at point here is the heat in, and heat will flow in two direction. So it will flow, it will transfer heater to the outside, another one will throw this direction, so this one is QA, this one is QB for per unit length. So total heat required will be summation of QA plus QB. So energy balance, about control surface of the heater. So heat input per unit length will be the summation of heat flow towards the A and towards the B. Okay, then we will find out individual, say this one, then we will add them together. Okay, towards the A, it will be the heater temperature minus inner tube inner temperature and the thermal resistance. So here, so Here will be the say for related to this circuit, the QA. So will be the total resistance between this circuit. It's a log R over Ri divided by 2 pi k. So all of them are given. So temperature at heater is 25, inner temperature given. How much given in a temperature? The 5, and log outer radius given 75 millimeter, and inner radius given 25 millimeter. You can keep millimeter because it will be unitless. 75 millimeter and 25 millimeter, each other will be cross out. Then 2 pi k is given 10. So from here we will get the heat loss towards the inside is 7 to 8 watt per meter. Okay, now for in other direction, say for this area, to related to this area, say Q towards the heater to the fluid direction, say will be the T heater temperature minus the fluid temperature divided by total resistance for this portion circuit. So here we have only one. Here will be the convection. So 1 over S pi then diameter, outer radius, also outer tube diameter. So now here this one given 25 and outer fluid temperature given -10, and convection heat coefficient is given 100 pi, and diameter outer is given, so radius given, so 2 times outer radius, so 75 millimeter. Okay, now here kh unit is given as a watt per meter square Kelvin, and so we'll make, so this one will divide it by 1000, it will become the meter. Okay, now if we solve this one, so we'll get heat flow through towards out heater to the fluid direction equal to 1649 watt per meter. Okay, so so heater power per unit length is required to maintain the heater temperature is 25, so it will be summation of, so for per unit length heater power required, so 728 plus 1649 equal to 2377 watt per meter. So this amount of heat is required for per length for heater to maintain the heater surface temperature 25 degrees Celsius. So this one is answer. Okay, I have one more question to solve. The next one is this one, last one. Yeah. Okay, so this one is problem related to annealing process. This process used to make steel less brittle. So first preheated the steel, then cool the steel to make it the less brittle. Okay, now there's some consideration given. So consider the preheat stage for a 125 millimeter thick steel plate. That means this thickness is given say 0.125 meters. So from the midpoint to the any side length will be 0.0625 meter. Okay, now density of the steel is given. So rho is given 7,830. Also C given 550. Thermal conductivity is K given 48, and which is initially at a uniform temperature. So initial temperature for steel given 150 degrees Celsius, and it is to be heated to a minimum temperature. So this on the minimum heated temperature given, say T, what I can find, T2 is given 550 degrees Celsius. Now heating is effected in a gas-fired furnace where produce the combustion at temperature. So your furnace temperature given 850 degrees Celsius and convection coefficient given 200. So here H given 200 watt per meter square Kelvin for in this on the related to the furnace in the both surface. So this on our steel and the both surface we have the temperature and the so hot air. Okay, now how long the plate should be left in the furnace? So basically we will find out the required time. So how long time will be required if you want to make your steel from 150 degrees Celsius to the 550 degrees Celsius in this environment, in this furnace internal conditions, a final temperature. So based on this condition, how long will take to reach a steel at a 550 degrees Celsius? Okay, so first we'll find out the that means this one is time dependent problems, so it will vary with the time. So now we'll check the byte number. So here the thickness. So thickness for rectangular plate 2L. So total thickness is given 0.125 meter. So effective characteristic length say LC will be same as length equal to 0.125 divided 2 will be 0.0625 meter. Okay, then Now we can calculate the Biot number. So BI, its formula is convection heat coefficient, then effect characteristics length LC divided by the thermal conduction coefficient. So here H is given 200 and LC is 0.0625 and K is given 48. So we will get the 0.26, which is greater than 0.1. Now for in this condition, we can't use the lamped system analysis. So therefore, better not to use lamped system analysis. So we will use the transit one-dimensional model to solve this problem. Okay, so transit one-dimensional model. Okay, now for this model, so we can solve from the chart. Also, we can find out from mathematical formula. Okay, so I will solve therefore based on chart. By using, if I solve this problem by using chart, basically the Isler chart. So in Isler chart, so let's show the Hitler chart. Okay, so these are the Isler chart. Y-axis is the dimensionless center line temperature. So there is a formula we can calculate dimensionless center line temperature from this formula. So T naught minus T alpha Ti minus T alpha. So this one is for y-axis values. It is called the dimensionless center line temperature. Okay, so here so if I use the given values, so we will reach at 550 degrees Celsius and furnace temperature given 850 and still initial temperature is 150 minus furnace temperature is 850. So from here we'll get approximately 0.43 the dimensionless centerline temperature. Now from this y-axis, we'll find out the 0.1 0.43. So here is a 4, 0.4, here 0.5. So it will be in between these two, say around here. Okay, now there is so many lines is given. These are basically the your inverse of your Biot number. So our Biot number is 0.26. So 1 over then Biot will be the equal to how much? To be equal to 3.85. Now there is an inverse Biot curve. So this one say for 6, this one 4, this one 3, but our value is 3.84. So will be between these 2 points. Say around, say this one is a half, say around this way. So we can draw one line. Say say yeah, so I can draw one line here, say for 3.85. So it will be this line. Okay, now another from the y-axis 4.4 dimensional center line below is 0.43. So it will be around here. That means this one is common point. Then if I draw the one line from here to the on the x-axis, it will be around here. So these are the common points. So corresponding our tau value is each point, each is between 3 to 4. There's a 5 portions. That means here will be 3.8 and here will be 3.6. In between these two, so we can consider our this parameter, say alpha t over length square. Basically it is the characteristic length. So LC equal to 3.7 from this Hissler chart. Okay, now we have this one from the Hissler chart using our dimensionless center line temperature, also the Biot numbers. So we can say alpha t over LC square equal to 3.7. Now here this alpha we can calculate from this formula, say K over density then C. So now if I put here this alpha, say K rho C and LC square, and here is the T equal to 3.7. Now if you rearrange for the time T, so 3.7 rho C LC square divided by K. Okay, now use the all given values. So 3.7 density given 7830, C given 550, characteristics length we calculated 0.0625 square divided by K. K is 48, so it will be the 297 second. So we should, the plate should, so the plate So plate should be left. So 1297 second in the furnace. So we use the chart to find out how long we need to keep the steel in the furnace to reheat it to 550 degrees Celsius. Okay, now I will show you another method uh, using the formula. Okay, so let me say method, another method. Okay, so this one also the tangent one dimensional model. So we know so different methods. So we know the tangent one dimension solution. Say one term approximation for center wall. The center line wall is formula is A1 E minus gamma lambda 1 square F naught. Now the center line temperature, this dimensionless center line temperature we can calculate from the formula I already used for the first method. Say the again if I solve this one, so dimensionless center line temperature, say theta naught will be the T naught minus T alpha T I minus T alpha, and it was 0.43. Okay. Now we'll use the table 4.2, this one for the plane wall, and we'll use this one for so let me show you the table one. So this one our table. So in our problem our byte number is 0.26. Now for 0.26 we will find out the A1 and lambda 1 value for the one terms approximate solution. Now our byte point is 0.26. Here is a given as a 0.2, 0.3. That means in between these two alpha. So first one, this one for the wall. So from this table, based on our byte number, value will be in between these two row. So if I calculate the say A1 between these two value, say 1.03 1 1, this one for the 0.2 byte number, so plus, so 1.0450 minus 1.0311, then times 0.6 divided by 0.1. So basically in between difference is 0.1. So this value, so is value 0.1. So total difference if we divide it by 0.1 we'll get for the each small elements, then times 0.6. So yeah, so it will give us say around 1.0396. Same thing for lambda 1. So first one is 0.4328 plus 0.5218 minus 0.4328 divided 0.1, then times the 0.6. It will give you, so lambda 1 for byte number 0.26 is 0.488. So we got our A1 and lambda 1 for the byte number 0.26. Okay, so A1 we got 1.0396 and lambda 1 we got 0.488 for byte number 0.26 using table 4.2. Okay, now from here, from equation 1, in equation 1, say from equation 1, if I use the dimensionless central line temperature, this value equal to A1 and say E minus lambda square, then F naught. So if I take, so we can write down 0.43 over A1 E minus lambda square F naught. Then if I take the log in both sides, so it will be negative F1 square and F naught. Okay, now say F naught will be the negative, so we can write down 1 over lambda 1 square, length 0.43A1. Now lambda 1 from the table we got 0.488 square, then log 0.43, and A1 we got from the tables 1.0396. In the same time is here F naught is alpha T over LC square. Now this alpha we already calculate for our method 1. From this formula we calculate already alpha from this formula k rho c from the method 1. So you can solve again because k is given, rho given, c given. So we'll get 1.115 10 to the power negative 5 meter square per second. So we will find out basically the t, so time. So it will be the LC was 0.0625 square, then alpha is 1.115 10 to the power negative 5, then negative, we can write down like 0.488 square, then log 0.43 1.0396. Now if we solve this one, we'll get the time around 1299 seconds. So we have to lift our steel up to 1299 seconds to reach 100, to preheat to 100 to the 550 degrees Celsius. This required time is this one. So for here is around 1299. Based on our chart method, we got the same around 1297. So you can use any method to solve this problem. So this one is tangential steady state problem. It's a tangential one-dimensional problem because problem is depend on the time. So there's a two method, you can use any of them to solve this problem. Okay guys,